Okay, here we are with section 6.2, the normal curve. Certainly the most important topic in statistics, although we have several topics in this class. Hard to say what the most important one is. It's probably several items tied for first. But either way, we thought we'd review what we saw at the end of 6.1 last time. And what we have here is what turns out to look basically like a bell curve, even though we didn't even think about it at the time. But if you kind of put midpoints into these tops of the histograms, like the tops of the buildings or something, and then start to connect them with sort of a smooth curve, and there are algorithms that do that, we look and see that it's approximately a bell curve, like that, more or less. And although I'm writing at an angle. And yeah, so these averages that we've taken very often turn into what we call a bell curve. And it's the hallmark of a normal distribution. That's its name. The fact it's called normal, normally in this case, it makes it very, very important. It's by far the most important distribution out of at least 30 that are out there. I'm sure there's probably hundreds if you really look carefully, but we had to memorize 30 of them ourselves. But, this is just the way it goes, and we could go into more detail, but that's not really that appropriate for the class. But we do have this example that we hinted at last time. This one separate from the coin flipping event, although this type of shape shows up in many, many circumstances. We can take a look at something independent of the coins. We can just look at the height of males. The median, or really mean height of adult males in the United States is 69.1 inches. That's, of course, 5'9", using the feet and inches notation, but a little bit more than 5'9". So if you're just right around 5'9", you are an average height adult male in this country. And if you're above that number, you're on the high side of it. If you're below that, you're on the low side. And one could get approximate readouts for taller people, such as an 80-inch person over here. That's going to be, 6'8", 72 taken away from the 80, get 8 inches. If you're 6'8", you're very tall. And there are not many people who are taller than you, although we don't pay too much attention to the Y scale, because you would really need histograms to make it in full effect. But that's going to be incidental. The Y scale is sometimes given. We just don't happen to pay much attention to it. So moving along, we take a look at some other characteristics. And we looked at mu plus or minus a sigma. In other words, the mean plus or minus 1 standard deviation. And it turns out that 2 standard deviations is a better measurement, and that's where we're headed here coming up in a minute. Most data is clustered about the mean. Yeah, most data sets are unimodal, in other words, one peak, and they cluster towards the middle. Now, I can't say every single distribution does that. There's some notable exceptions, but they're comparatively rare, unless you're in certain situations that you would be prone to see them. But most people are not usually in that kind of mode. But they're saying here the vast majority of adult males are within a few inches of the mean. So we take a look at 5 inches of the mean. If I can get this to underline. 95% of adult males shaded in yellow are within 5 inches of the mean. So it's a little hard to see here, but that would be 69. I'll just round to the nearest inch. And if you add 5, that would be to 74. If you subtract 5, you'd be down to 64. So between 64 and 74, which is approximately there and there, 95% approximately of adult males are in that range. So putting it into feet and inches, as most people relate to, that would put men between 5'4" and 6'2". So if you convert, not too hard to do. I'm not going to go into detail here, but I said 5'4", sorry, and 6'2". And so if you're in that range, you're in the middle 95%. If you're not in that range, then you are in the outer 5%. And it turns out that could be split 2.5% per. So above 6'2", you're in the top 2.5%. If you're below 5'4", you would be in the lower 2.5%. And that's what they're aiming at over here. lower and higher, and that would leave 5% left over. 100 minus 95 is 5. And if you're looking at each individual tail, as they call it, although they didn't make this look very symmetric here, that would be 2.5% apiece. I'll just say each, so I don't have to write it twice. And we do have a symmetry of sorts, and they're showing it. In fact, with the ones that I just looked at, I guess, well, actually not quite the ones I just looked at. They're looking at, say, if you have 5'9", let's just round it to 5'9", 5'9". And then we would have going over 2 inches this way, 5'11", going 2 inches that way, you'd have 5'7". All they did was they added 2 inches, they subtracted 2 inches, and we see that we have the same proportion at that level. So 13 adult males in millions, but that's not a big deal here. We're not going to be really paying very much attention to the y-axis. That's done in more advanced classes because they're making it look simpler than it really is, to be honest, and we're not going to go in that direction. Just I'd be level with you here. Now, how do we get to 6'4"? Well, we go from 5'9" to 6'4". That's going to be an additional 7 inches. So they move that over 7 inches. And if you subtract 7 inches, 5'9" minus 7 inches is 5'2". So there's a little bit of scratch work there, and that's where they got that value there as they moved back 7 inches. In other words, they're just trying to show you the symmetry. For any inches you move away from the mean, you have a symmetry as far as totals are concerned. So this would be at the level of, let's see, that's 5'2". These are very low, less than 1%, 6'4", less than 1%. But that, as I say, we're not going to be spending any real time on the y-axis. So the bell curve is definitely symmetric. That's one of the best advantages. There are many distributions that are symmetric, but they may not look like this. The curve to the left of the mean is a mirror image of the curve to the right of the mean. In other words, if you put a mirror right down the center, you should see the same thing. Or in reality, it should be approximately the same thing, such as with the coin flips. That was not perfectly symmetric, as I flash back here. Not perfectly symmetric, but close enough. I was trying to draw that out. One part that was a little bit of a weakness was here versus here. That was off by somewhat, but if you just step back and take a look at it from a distance, it doesn't look that different after all, does it? So that's what we're talking about, at least approximately symmetric. In terms of heights, there are about the same number of men 2 inches taller than there are the same number of men 2 inches shorter. As long as you have the same 2 inches, it doesn't matter if you're going forward or backward 2 inches, you still have the same likelihood. Of course, the highest likelihood is right in the middle, 5'9". And to be more accurate about the percentages, you would have to create a bar chart, but we're not prepared to do that. That's not in the cards for us. They'll be doing it coming up, though, a little bit. So if it's normally distributed data, which happens a great deal of time, I don't have any percentages, but it's a vast majority, I'll put it that way, then because it's normal, it's bell-shaped. Technically, a bell shape doesn't guarantee normality, but normality does guarantee a bell-shaped curve, whatever. That's a minor point. The mean and median are approximately, I'll put an approximately sign, the same, because in the real world, they rarely work out to be exactly the same, but in theory, they would be. There's a difference between the theoretical curve and what really happens. The theoretical curve is just about impossible to obtain. It's like hitting a bullseye every single time. But if you're relatively close, and there are tests for these things that we don't talk about, you could say, yeah, we have approximate normal, and virtually the approximate is kind of scrubbed out because it's kind of obvious that it's approximately normal. And then we just go and use the properties that are within reason accurate. And they're very much thought about and written about. We're only going to skim the surface of that type of methodology. Most of the data, of course, is near the mean. That's obviously the case. Data are symmetrically distributed above and below. We just kind of said that. So, yeah, symmetrical. And that happens quite a bit too, at least approximately so. And so, here we have a couple of examples. The first example, figure 6.17, shows the distribution of IQ scores. And notice if you look carefully, I don't know if I can zoom very much here, but yeah, you can zoom a little bit. And you can see it, they've made it up of a whole bunch of little histograms, little histogram bars. And so the story goes, the finer and finer, as you shrink the width of the histograms and make them tinier and tinier and have more and more histograms, it starts to become a smooth curve. And that is a calculus argument that we're not going to really explore, but they are kind of hinting at it here a little bit. And so as we get kind of the perfect centering here, we see the IQ scores. 100 would be the mean according to their methodologies, and usually a standard deviation is 15, but that turns out to not be that important right now. And let's see, I guess I need to drag these down, so we can actually read it. I'm playing with the graphs here. Okay, so first was IQ scores, which is clearly normal. But then the next one, figure 6.18, is percentage of American families and level of income. And which one is normally distributed and why? Well, as we just learned, that is clearly the bell curve. And what is this? Hard to tell. And there's a couple of issues with it too. The number of families in percentages and population percentages, this actually works out much better now because we actually do have a finite width for all the histograms, whichever graph you're looking at, either the left one or the right one. Whereas a smooth curve, well, does need a little more work to actually determine the percentage, so that would not be something we would care to do. In fact, we're not going to really be doing it much here anyway as far as this is concerned. We've got another idea for you. But the second graph has problems, and two that stand out to me are these last two categories. They're counting by tens of thousands, from basically 0 to 10,000, 10 to 20, 20 to 30, 90 to 100. All those are by tens. And then suddenly they go by 50s, 100, 150, 150 to 200. And so this one especially would be called into question. They've changed the scale. But even then, it's not a bell curve. Yeah, certainly it starts off a little on the low side. Not that many people, according to this is probably like 7, 8 years old. Well, not many people earn less than 10,000, but lots of people earn between 10 and 20. And then it just starts to taper off in a regular way. It would be nice to see some more of the data, but I just imagine it'd be headed down the ladder or down the stair steps and to the point where, the more you make, the less apt you are to actually do that. So there are some very, very rich people, but there are not very many of them. Lots of people earn a moderate amount of income or a lower amount of income, and the more money you make, the less apt you are to find neighbors, that's a bad word, but people in the same position as you, because it just becomes harder and harder to do that statistically. So anyway, this is not a normal curve, and the left one is. It's a bell-shaped curve, and so you can see the symmetry. The 100 is the center, and it just fans out evenly. The 110 is symmetric with a 90, for example, because it would go 10 units in either direction. You can even go out to 40 units in either direction, 140, basically genius level, and then 60. And those are symmetric too, both way less than 1% of the population. Whereas at 100, you would find around 2.7% around here. So yeah, you could predict that. Whereas the income data probably would be shifting from year to year or decade to decade, but still, it's not even close to a bell curve. It's skewed. We're not really getting into skewness, but it's certainly not symmetric. Anyway, they reiterate what I just said, and they're symmetric. The IQ scores are symmetric, and the median score, mean score is 100. That's by definition on an IQ test. And although they've been somewhat discredited, they're trying to seek the level of, where maybe a college student might have an IQ of 110 on average or even higher. So I dare say that many of you are in that category, which is wonderful. But it tends to stereotype people too, and I've not been a fan. I had an IQ test a while back, and I was definitely stereotyped and did not appreciate that. So I understand the weaknesses involved, and I think they're working on that kind of thing and doing better as they go along. But besides that, family incomes do not appear to be normally distributed, and so that is not symmetric. The more you make, the less apt you are to find people in your same bracket. It's just you get to $1 million, and not many people are there. There are some. You can find them, but they're not anywhere near a decent percentage of people. It's a much, much smaller percentage. It's skewed towards the lower end of the scale, meaning there are many more families with low incomes than with high incomes. So that's an important thing to notice. And not that we're talking about any particular category for any reason. We're just saying that that is not a bell curve. That's a very famous example of non-normality, in fact, when you have situations that are not at all bell-shaped. So yeah, you can have bell-shaped stuff and stuff that isn't. Income level, economic statistics, those are all help with the median and the box plots and things like that. Typically, if you're going to a box plot, either you don't know what the distribution is, you just don't have any really inkling about it, or you have a reason to think it's not normal, like real estate levels, housing markets, or income data. Those are almost always non-normal. It's really hard to find cases where they are. It's possible in certain areas of the country, but it would be very unlikely. It probably wouldn't last very long because they just don't collect in the same way that normal data does. So we do have exceptions to the normal situation. Let's take a look at some of this other stuff now. We have mean and standard deviation for the normal distribution. In a normal distribution, the mean and standard deviation completely determine the bell shape of the graph of the data. So if we realize we're going to be using the normal model, all we have to have is the mean and the standard deviation. In fact, we don't even have to draw it, but it's always a really nice idea to do that. In my statistics classes, especially in the beginning, I always insist on drawing a curve. And I can certainly do that on a test as well. So that's why your PDF is so important, because you just can't draw that on Blackboard. But we'll have further announcements on that later. And I'm working on the test, getting them done. The mean determines the middle of the bell curve. That's kind of obvious. I don't even need to circle that. But the standard deviation determines how steep the curve is, or how flat the curve is, you could say. A large standard deviation results in a very wide bell, and a small standard deviation results in a thin, and they call the word steep bell. So we have one of each. Both of them have a mean of 500. I'll use the Greek symbol mu for mean. They both have that, but what they don't share is the standard deviation. Here, standard deviation is 100. And over here, standard deviation is only 50. And it looks, you can see a major difference in just the way they look. And it's nice that they kept the same scale too. I noticed the scale goes from 200 to 800 in both cases. When you change the scale, I've seen lots of books who change this kind of thing up and say, oh, look at the thing. And then the curves look the same because they changed the scale. It's like, what? You can't do that. You've got to keep the scale the same. If you're comparing apples to apples, you want to keep the apple scale going. You don't want to change it to the orange scale. That wouldn't make sense. So anyway, getting back to this, you see that they moved one standard deviation in each direction from the 500. 500 plus 100 is 600. 500 minus 100 is 400. And they're just showing where the middle 68% lived, middle two-thirds approximately, like we hinted at before. We'll come back to that. But now, if you only have 50 to move to get to one standard deviation, then you have 550 here and 450 there, and it's much steeper because it still has to contain the same amount of area. As it turns out, what they'll say is the area under every curve is considered to be 1 or 100%, and if this is 68%, it's all flat and pancaked kind of, and whereas here it's more like squeezed, and to get to the 68% we have to move up the ladder quite a bit. And although I don't really care about the 0.008, look how different that is than 0.004. I'm just looking at the comparisons. We're not going to be using those numbers officially, but it does show you how we had to rise the curve up to encompass more area. If you've got less width, you have to have a higher height if the number of people are the same. So if we had like 1,000 people or 1,000 coin tosses, whatever it might be, 680 of them would have to be in this window, 68%. And whether it's flat or whether it's steep, that almost doesn't matter. But the mu and the sigma, the mean and the standard deviation, have to be given. And then sketch is sometimes considered redundant, although I love my sketches. Okay, and here is what is called the empirical rule. I'll go ahead and put a name on it. But if you like the numbers, it does tell you what the numbers do. And the normal data is the 68, 95, 99.7 rule. And given normal distribution data, or at least approximately normal, about 68% lie within one standard deviation of the mean, 34 on each side. I'm not going to really worry about splitting the difference too much. 34 above, 34 below, so about a third each, a third below the mean, a third above the mean, and then that window that we've looked at a couple times now is going to give you about 2/3 of the data, which that would be 67%, so we have 68%. Probably the most important one is this one. Although we don't have much time to go into this, this is the one that's heavily used. Around 95% of the data is approximately 2 standard deviations from the mean. Technically, it's 1.96. We're not going to have to go that distance here. And yeah, you could split the 95% in half and get 47.5 in each side, but I don't really pay that much attention to it. That's not going to particularly help us. Here's one that's kind of odd, though. If you're within 3 standard deviations, you're talking about 99.7% of the data. That's all but 3 in 1,000 cases. So 997 cases out of 1,000 are within 3 standard deviations. And typical tables only go to about 3.5 standard deviations, because at that point, it's really close to 0. And there's 0 probability. And so they just kind of say, hey, there's no reason to continue a table out. And most people use technology anyway, but we're not going to be getting to that point in our class. So that's going to be kind of a moot point. We'll be giving you a table, but I don't think it even goes out to 3.5. Because we have a much smaller table than many classes get, because this is just meant to be an overview, just a kind of a glimpse of the material. Okay, so let's take a look at all 3 of them, the 68, the 95, and the 99.7. I know these are a little small. Maybe I can increase the size just a little bit. Okay, so the 68% is within 1 standard deviation. So they have not given us numbers. You can imagine any numbers you wish, whether it's 500 and 100 or whatever you want. But 68% of the data shaded in green is within 1 standard deviation of the mean. So that's a big chunk, but there's a lot left over too. The one that's seen the most, at least in the statistical world, is the 95% of the data. That seems to be a good number for lots of reasons that we may not have time to go into. But within 2 standard deviations of the mean, we've got all but 5%. 95% is in the middle. So we have really 2.5% out in what we call the tails. And there are some people out there, there's a lot of people that are not in the middle on that kind of labeling. But if you are talking about 99.7% of the data, now you're talking a vast amount of data, and very few people or cases will be in what's left of the tails. There is a little bit left. 0.3% divided by 2. We're talking about a small amount of data. About 1.5 out of 1,000 on each side. Totaling 3 out of 1,000 would be outside this huge window of opportunity. And so this is within 3 standard deviations of the mean. Okay, so let's put some numbers on these. I don't see any reason to go to 2 decimal places on this much, but they did. Now we look at the example we had before with the mean of 69.1. And the standard deviation, well, they could have just said 2.7, but they said 2.65. That's fine, whatever. So adult male heights in the U.S. were normally distributed, mean of 69.1, standard deviation 2.65 inches, of course. And so what does this rule tell us about the heights of adult males? So 68% are within 1 standard deviation. So between 1 standard deviation, this is going to be mu plus a sigma and u minus a sigma, often bundled together to say plus or minus. So that's the symbolic way of saying it. So let's take a look at subtracting and then adding. I would add first myself, but if you subtract, we find that it's 66.45 inches, or on the high side, 71.75 inches, and they've also converted this to feet and inches, which is not completely necessary, but it can aid in understanding, so I would let you decide on that. We're never going to ask you to do that. I don't think even WebAssign does that. But if so, just divide by 12, and the leftover amount is your inches. That's really all it is. So 5'6.5" inches versus just about 6 feet, and that's me. I'm just at 6 feet. According to the Army, I was just a tick less than 6 feet tall. But that's no big deal either way. So I'd be in the middle ground there of the 68%. But then you widen that scope to get to 95%. Now we're talking 2 sigmas. So if I can turn this back on, get to 2 sigmas, and even use the terminology, perhaps mu plus or minus 2 sigmas. So they double the 2.65. They double the sigma, which of course is sitting there. And that gets us, what, 5.3? And then add either by hand or with a calculator. And we subtract first to get to 63.8 inches. And then we add the same number to get 74.4 inches. And if you really want to, we could say this is 5'4" 4 rounded. I think we looked at that already. And then 6'2", and that's also a rounded number. But now if you're talking about 3 standard deviations, now we're talking about almost everybody. So if we subtract 3 sigmas, which is a big number, it's about what? Almost exactly 8. It's just about 7.95. Okay, so you get to 61.15 inches. That'd be 5'1" for males. That would be considered to be a little on the short side, I guess. But then if you add 3 sigmas, then you're talking 77 inches tall. Subtract the 72 out, you're up to 6'5". And I know people who are 6'6". And basketball players are not always, but very typically taller, or several 7-footers, and they're 4 or 5 standard deviations above normal, which is just about off the charts, rare. But if they're coordinated, they may as well make a good living, at least for a while, playing basketball. But good for them. Anyway, let's talk about other examples that have nothing to do with height. Let's talk about apples. And weights of apples in the fall harvest are normally distributed. And then we go to the metric system and talk about the mean weight of 200 grams and standard deviation of 12. So the first figure, 6.28, shows the weight distribution of 2,000 apples. So remember, that's a very large number. And in a supply of 2,000 apples, how many would weigh between these two numbers here? Now, what you might not know right off the top is that they've picked a multiple of the standard deviation for us to worry about. And so that's okay. It's not so bad to do that. If they'd picked some other weird number like 173 or 229 or something, then we would have had to use further techniques that we haven't learned yet. But for now, we can just kind of leapfrog on or piggyback onto what we just learned. And so what we're going to do is take a look at the picture with 200 in the center, and we also go plus or minus 12 grams. And so we do that and find the numbers and seal off the 224 and the 176. Notice how close it is to this scale when they count by 25s. There's your 225, there's your 175. And yeah, we're very close to what they said, but that's okay. We just moved in slightly. As it turns out, this is 2 standard deviations away. Why do I know that? Well, to get to 224, we took 200 plus 24. That has the advantage of being a nice round number. And 24, as we kind of work backwards on this, 24 is equal to 2 of these magic numbers known as 12. 2 standard deviations. I'll just say 2 SDs or 2 sigma. And so that's what we have. We've got U plus 2 sigma and U minus 2 sigma. Just to double check that, if we take a look at the other side of the hill, so to speak, we'd have our 200 minus 2 of the 12s, which is, of course, 24. And that is equal to 176. And that's exactly what they asked for. So the trick on these types of questions, and you'll see a handful of them, is to see, is it 1 sigma, is it 2 sigma, maybe even 3. And there's only 3 possible answers, so pick one. Just see how that standard deviation stacks up to the difference between the mean. And I would go for the higher number. It's just a little bit easier to do. I would go for the right side. It's easier to add than subtract. So that's what I would do. And that's the only thing that's going on here. You don't have to get z-scores or a table or anything like that, because they picked some of the special cases in this sort of situation. So they explain in their own words how they did it. So they're going for the low side first. Yeah, they always have to do the hard one first. That's just the way books are. Apples weighing 176 grams are 200 minus 176, 24 grams below. So they went below first. That's fine. And apples weighing 224 grams are, as you subtract 200 away, 24 grams above the mean. And the 24 is in common. How about that? And then we look at the 12 and we think, how do we get a 24 into a 12? We divide it, and we get, of course, the 2 standard deviations. And so the weight range that they gave, 176 to 224, is within 2 standard deviations of the mean. And 2 standard deviations is locked in with the 95%, at least to the nearest decimal place. It's 95%. So that's how it goes. 95% of the data points will lie in this range. Then they take it a half step further. They're saying that since we have 2,000 apples, we can multiply 200 times 0.95, very easy on your calculator, and you get very close to 1,900 apples. We'll just call it 1,900 apples, way between those boundaries, 176 to 224. That also means 100 apples will be really big apples or really small apples. So 2,000 minus 1,900, of course, is that 100 that does not fit in the middle. So you got the big middle, and you've got the kind of the outliers, sort of, so to speak. And that's kind of the way it's treated too in hypothesis testing. You've got rejection regions and fail to reject regions, etc. That middle 95% is often where you go with the status quo. And you go to the outsides, you're rejecting the status quo. Just very quickly, a summarization, summarizing the hypothesis testing idea that we don't have time for. I wish we did, because I enjoy that kind of thing, because that means you're the umpire, you're the referee, you're the judge, and you get to make the call. But we don't have time for that in this class. In a normal distribution, we have this thing that I hinted at before. It's called the z-score, or sometimes called the standard score. Yeah, that's another way to say it. I use z. For a data point, it's the number of standard deviations that point lies above or below the mean. So we're talking in terms of standard deviations, above or below the mean. We'll explain that a little bit further here. For data points above the mean, the z-score is positive. That seems to make sense. For data points below the mean, the z-score is negative. And so we have here in English the most important formula in statistics, without a doubt. This is the number one formula. And so often the data point is called x. That's just a tradition. It just goes back a long ways. The mean is usually called mu. There is another name occasionally. And we're going to take that number and divide by the standard deviation. So there it is, x minus mu over sigma. I'll just write it in a more readable fashion. I hope you can read this. X minus mu over sigma, or simply the data point minus the mean. Find out how far it is away and what sign is it. Is it above, positive, or is it below, negative? Standard deviations are always positive, so they're not going to change the sign. The sign is controlled by the numerator. Standard deviation being positive, it's technically possible to have a 0 standard deviation, and then there would not be a z-score to calculate because all your data points would be the same. And then standard deviations can never, ever be negative. If you have a negative in your standard deviation, you have made a mistake and it's time to start over. If you're just blindly using a calculator, that would mean you really need to do it by hand because something has clearly gone wrong. But, of course, programmable calculators are not allowed here, too. So if you are depending on one right now, you need to wean yourself away from it and learn how to do it by hand because they are not allowed. Because as your steps are needed to be shown, I can always tell if somebody really knew how to do it or not. So in other classes, well, they allow them. It's a different ball game. But here we just don't have it around long enough. And Excel is not going to be of very much help here, I'm afraid. Now, the other way around is not seen as often. We do see the reverse situation. If you need to find a data point, maybe the data point is what you don't know, and you do know the mean, you do know the standard deviation, you can figure out the z-score, well, then we can kind of reverse the script. And I don't think we're going to have much use for this, very little use. But let me rewrite this in terms of something we can understand. That would be x for the data point equaling the mean plus z times sigma. So typically, this is used for like, what would it take to be in the top 10%? You look up a z-score for that, you multiply that by the standard deviation, and then you add it to the mean, and that would be your value. So to get in the top 10%, you might have to score a 27 on this big, say, police exam. That puts you in the top 10%. Wonderful. And if you're not in the top 10%, then you don't get to be a special officer of some kind. So whatever. That's one example that's always stuck with me for some reason. So here we have some examples, and let's take a look at them. The weights of newborns in the United States are approximately normally distributed. And in terms of grams, and also in terms of pounds and ounces, mean birth weight for single births, we're not talking twins, triplets, etc., it's about 3,332 grams. Too bad it wasn't all threes, right? But that works out to be 7 pounds, 5 ounces, and, it's a little less than 7.5 pounds. And so the standard deviation is about 530 grams. So if that's the mean, turn it back on, and you got that. You got the 530 is the standard deviation. It shows you how flat the bell curve is, or how steep it is, depending on what you think. Calculate the z-score for a newborn that weighs 3,700 grams. This baby would be 8 pounds, 2 ounces, which is somewhat bigger than normal, almost a full pound above average. So I used the word normal, I meant to say average. Okay, so let's see if we can find it out. Let's just get the z-score for that for now. So we do that. We find the difference, and you can use the formula or you can use the train of thought. That would be up to you, but you would need to find z is equal to x minus mu over sigma. So I'll show you the formula parallel to what they're doing. You could put in the 3,700 and subtract out the 3,332, and then don't forget when you're done to divide by the standard deviation 530. But they're breaking it down into multiple steps. They take the numerator and find that this baby is 368 grams above the mean weight, and that's a little less than a pound. And then we divide, as we're showing you here, by the standard deviation, which is 530. So you notice we have the same answers, just a slightly different path. And this book does not round to 2 decimal places. Every other book rounds to 2 decimal places. This book rounds to 1. So if you want to use the table, you'll have to round to 1 decimal place because it's a very short table, which is fine. We don't need big fancy tables for something we're only spending a few weeks on. And I completely agree with that. So 0.7 says that this baby is a little bit larger than normal. And one could even put it on a little graph here. If, as it turns out, in terms of z's, the mean is 0. So let me just say that. They didn't say it before, but when z is on the right side, z is positive. So as over there, we've got positive z's. On the left side, you've got negative z's. But in the middle, I'll put a little mu there just to reinforce that. We have a z equal to 0. Well, anyway, the 0.7 is somewhere over here. So I'll just put a 0.7 there. So this baby is above average. And then you can do the same graph exactly with a scale of grams. You can put the 3,332. It's getting very cluttered, I realize. And then you could stick a 3,700 over here. The page number got in the way. Cross that out. And see exactly the same thing. So whether you use the gram scale, I'll just put a little g there, or pounds, or weight, or whatever you want to put that down for. But the grams does have an advantage of being more further defined, more accuracy. The ounces, plus the pounds with the ounces, looks really awkward. It's better to just pick one unit and stay with it. You could total a number of ounces, and that wouldn't be much of a problem. But this is slightly more accurate, I guess, with more digits, I guess you could say. Well, anyway, this baby is 7/10 of a standard deviation above average, being a positive number. Okay, so now we do have this table. And yes, the table, if it's necessary, I will include it with the test, although I can certainly write questions like what we just had and not even ask for further information. I've done that before too. So this recalls that we have to look at the percentile, and I've kind of chopped off the very bottom part of the table, so let's see if we can get there. Recall the percentile. And do they do that on the next? Yeah, they do it on the next page, so I guess I'll just let them define it. So we'll come back to this table in just a second. The percentile for a number relative to a list of data is the percentage of data points that are less than or equal to that number. Okay, so that's what we can look up. And let's go ahead and use the other table. I can try to expand it just a little bit. And we found our z-score of 0.7, so let me try to circle that. This puts that baby in the 75th.8. You can just call it the 76th percentile. I'll just round to the nearest percentile. 76, I'll just write it percentile, a little abbreviation like that. And yeah, this baby is ahead of 76% of the babies out there. 75.8 to be exact, I guess you could say. Although this z-score being rounded, you could get a better approximation on the percentile, but we're not going to be concerned with that kind of detail here. So yeah, this is on a scale of, say, 0 to 100. This baby is 76th, further to the side because they're bigger than average, larger than average. Let's see how the table could be used for another problem. And this one has to do with flu patients. This is way before COVID. And anyway, the average length of illness for flu patients, and I heard, by the way, the incidences of the normal flu is way, way down. We're talking about just a few hundred cases. Was it in California or the entire country? And they usually get tens and tens of thousands, hundreds of thousands of flu cases. Not many people die from it, but some people do, and some people get really, really sick. But it's down to just hundreds now. because everybody's more concerned about the bigger picture. Picture right now is the COVID, obviously, and flu has been kind of pushed aside. But people still get it once in a while. So hopefully we'll go back to the times where flu is the worst thing we have to worry about. That would be nice. Hopefully that'll happen. Average length of illness for those patients in a season is normally distributed. The mean is 8 days. And the standard deviation, well, too bad they couldn't call it just 1 day, but 0.9, a little bit more accurate there. What percentage of flu patients will be ill for more than 10 days? So kind of unlucky. Here's a case where the larger number is worse. It's kind of like golf and the baseball ERA. Sometimes the bigger numbers are not good, but we can still measure them, and it's still to the right of the curve. But maybe this is where you wouldn't want to be there, because if you get the flu, you want to get over it as fast as you can. Well, anyway, we could get a Z formula going, and I'll write down the formula and put in some numbers, and they're going to do it English style. And what we have here is a value of 10 days. That's going to be our X. So I will put in the 10. And then we're going to subtract away the mean and find that this is going to be at least 2 days above average, which is a bad thing. The standard deviation was 0.9, or 0.9 if you prefer. So this works out to be 2 over 0.9, which is about 2.2. And that's what they're explaining in their own style here. They're just avoiding the formula. I'm more of a formula person. So anyway, 10 days is 2 days above the 8 days, and so the z-score of 2 over 0.9 is 2.2. According to our table, that's as far as we need to go. And let's check it out. For 2.2, it's over here, and we're down to 98.6, or say the 99th percentile. So I'll keep it with the decimal there. I'll just round to 1 decimal, though. With me, it's a little inconsistent to have a single decimal for the z and have 2 decimals for the percentile. Excuse me, how do you get that again? You're trying to get more accuracy than you can possibly get, but that's just a minor quibble here. Otherwise, the book is doing a fine job of doing an overview of statistics. We're not going into too much depth, believe it or not. Table 6.2 gives a percentile of about, that's certainly key, 98.6%. That's a coincidence for the temperature number. And this means that about 98.6 patients will recover in 10 days or less. Yeah, so that's what's happening. And then, if you're looking at worse than that, to flip the script, you do have to subtract from 100. And this is where a sketch, I believe, is of tremendous use. As you subtract the two numbers, we're down to only about 1.5%, 1.4, will be ill for more than 10 days. So here's what the sketch would look like, and hopefully this will shed some light on the picture. So I'll draw a line down the middle for the mean. And the mean is 8. And these peoples would be above 10. So I typically shade in that area. It's a little bit shaded. So we're looking at x not just equal to 10, but x being greater than or equal to 10. Or just more than. So strictly speaking, actually it does not matter for these curves whether you put the equal sign or not. So greater than 10, the idea is to find the percentile first. The percentile also will always go to the left. It's a cumulative number. It's a left-moving type of statistic. And so when we plug the number in, we find that gives us 98.6%. But that's facing the wrong way. Remember, they did say more than 10 days, not less than. The table is always a less than table. All tables are less than tables. In fact, calculators are set to be less thans as well, because cumulative running totals so far is a big deal. It's a big deal. But if you ever want to do the other, you just subtract it from 100. And yeah, so we do that, and we find the 1.4%, which was indeed the answer for people who are sick for more than 10 days. It doesn't say what the upper limit is, but that's no big deal. Hopefully it's not much longer than 10. But anyway, those are the unlucky few, unless you just like being sick, which I can't imagine. Nobody likes that. So that would be the worst 1.4%. Upper 1.4% is not necessarily the best. So that's an interesting idea. Okay, we're getting close to the end here. Let's see what we have left. Recall from previous examples that weights of newborns in the United States are normally distributed approximately, and we had the 3,332 grams for a mean birth weight. with a standard deviation of about 530 grams. So now, on this scale, what percentage of newborns weigh more than 8 pounds? And I don't know why they went to tenths here. 36 would have been fine. What percentage of newborns weigh more than 8 pounds? So before we get to question 2, let me just jump ahead and see if we can explain the answer for number 1. Okay, so we have x minus mu over sigma. So this is your x. This is your mu. There's your sigma. And they put the numbers in. They found that 3636.4 minus 3332 gives us a gap or a number that's higher than average by 304 or so grams. Dividing that by 530 to standardize it, to talk about number of standard deviations, and rounding to the nearest tenth, we see that gives us 0.6 for the z-score. Okay, that may be the case, and then, well, that is the case. I've double-checked all of these, and so then we go back to the table. Let's check out 0.6. It's just above the 0.7 that I circled, so I just kind of put an arrow there and put an arrow there. It's about 72.6%. You could say 73rd percentile if you'd like, but what they're going to do is they're just going to keep the 72.6%. Okay, but what did the question say? The question said more than. Oops. The table is always a less than table. So the table is less than. So that means the 72.6% of the newborns weigh 8 pounds or less. A big star there. So yeah, that's facing the wrong way. And this is where the curve might help. And I've always been a big fan of it for standard statistics classes. Well, of course, our mean was 3332. And the cutoff value we're interested in, which is all we actually get, is 3636. Let me just put it here, and I'll just round to the nearest whole number. And we're interested in more than that. So once again, just like last time, the table goes the wrong direction. About half the time it goes in the wrong direction. Half the time it goes correctly. So here we had 72.6% that are less than that target number. And 100% minus 72.6% gives us the number we're actually looking for, the upper 27.4%, which is what the table doesn't directly give us. It just gives it to us indirectly. It wants to face to the left. We'd like to face to the right here. We have to subtract from 100%. That's something that you just have to know. So please practice it until you understand it. Very, very important concept in statistics, by the way. So don't think it's make work. This is actually critically important. Let's take a look at the second case. Low birth weight is a medical concern. The American Medical Association defines low birth rate to be 2,500 grams. That'd be 5 pounds, 8 ounces. I believe my sister was that low. So anyway, 2,500 grams or less. What percentage of newborns are classified as low birth weight babies? Okay, so they put in the 2,500, they put in the mean, they put in the standard deviation. Those numbers are exactly the same as before. Actually, this is a mistake. We've got to reverse these. Okay, so we put the 2,500 in first, like they did correctly there. Subtract the 3332. The 832 is correct, but it is a negative. That means we have a negative 1.6 and a negative 1.6. So there's some mistakes there that I'm correcting now, because low birth weight babies indicate a negative Z because they're below average, period. And I'm going to do a sketch to try to reinforce this. There's the 3332 right down the middle. We have the 2,500 over here somewhere. Don't really care where you stick it. But that Z-score is a negative 1.6. But this time, because we're interested in those that are 5%, what was the question say? It says low birth weight babies. It does say or less. And at least that's the way the table's facing. So that's good news. We're facing the same way the table is, which is a little bit easier. So we just look at the value of minus 1.6. What does it say? Negative 1.6 is only in about the 5th percentile, 5.48. So they're saying as they round it to 5.5, 5%, 5.5% approximately of newborns are classified as low birth weight babies. So that's good. So anyway, it's not good, I should say, but at least the number is low. That's the good part of it. I must have misspoke there. So, yeah, we have about a 5% chance of having a low birth weight baby. That doesn't mean necessarily the baby's in trouble, but it means they need to be closely watched. And of course, the smaller they get, you hear about cases on the news where they're even smaller than that and they come out okay. But they have to be monitored carefully because there's always a danger that they may not make it. So that's something that's very, very serious, obviously. So this is how the table can be used. We're taking it one extra step. We go from the data X into a z-score, and then using a table, we find a percentage or percentile, or even sometimes a proportion on your calculator. So that's the overall plan that we're going to be using here. It's really a two-step plan. You've got your data, X. You convert it to a z-score by the major formula, and then with a table, sometimes with technology, you can find the percentage. And that's it in a nutshell. Very, very important core of statistics right there. In the overview, we could not skip this. Okay, I guess that'll do it for today. This is for the lecture for Monday and Tuesday of this week. I guess that's 15 and 16. And we'll be back live on St. Patrick's Day. There's Irish music in the background. And then on the 18th as well, depending on what section you're in. So stay warm, and we'll talk to you very soon. Bye-bye.